In this block of material, we're going to look at 4 specific probability distributions. We've been talking about the basics of probability and about discrete probability distributions for discrete random variables. Here now we're going to take a look at 4 very useful and very specific probability distributions that 2 of which are discrete and 2 of which are continuous. And these are probability distributions where the probabilities can be calculated specifically from known mathematical functions. And we will get into this in some detail. Just as an overview again, we are actually looking at our block of material now on the normal, binomial, Poisson, and exponential distributions. Our objectives here are going to be to understand these distributions and to perform probability calculations and calculations based on the probabilities for these 4 distributions. And I'll focus on the binomial distribution first and then the normal distribution. I tackle binomial first because it's a discrete probability distribution, so it's somewhat of an extension of the material that we've just covered in our previous block of material. The normal distribution is a very powerful and extremely useful distribution, and it's really going to be the basis for everything we do going forward in inferential statistics. It's a continuous distribution, and we'll tackle that one next. The Poisson and exponential distributions are 2 others that are extremely useful in many arenas, and it turns out the Poisson is a discrete distribution and the exponential distribution is a continuous distribution, but the 2 are very intimately connected, and we'll see how that plays out as well. So let's talk about the binomial distribution. It is, as I said, a discrete probability distribution, and we describe the discrete probability distribution as a listing of all the possible outcomes from some event, all the possible values that this discrete random variable can possibly take on, accompanied by the probability of each one of those outcomes taking place. And it turns out in the binomial distribution, the probabilities emerge from calculations that are based on a specific set of circumstances. And these are defined as follows. If we have a scenario where we have some fixed number of independent trials, we're going to test something a certain number of times. And each time we test it, there's one of 2 results. Either we find what we're looking for or we don't. Either we get what we call a success or a failure. And there also has to be, thirdly, some known fixed probability of success, a probability of finding what we're looking for. A really good example we can quickly get our head around is if I were tossing a coin. And not just one time, but let's suppose I'm going to toss a coin 10 times. And the thing that I want to calculate, the variable in this case, is how many times do I get a certain outcome. Let's suppose I'm going to pick heads. And I want to know, out of 10 coin tosses, what's the probability that I'm going to get heads a specific number of times? Let's say 7 times. Okay, in this case, I've got a fixed number of independent trials. That would be my 10 coin tosses. The result in every coin toss is either going to be a success, meaning I got heads, the thing I'm looking for, or a failure, meaning I got tails. There's one of 2 possible outcomes. And there's also a fixed probability of success. There's a 50% chance, a known 50% chance that I'm going to get heads, and thereby also a 50% chance that I'm going to get tails. But the key is, every time I toss that coin, I have a certain constant probability of getting heads. Well, that scenario of looking for a certain number of heads out of some fixed number of coin tosses is an example of a binomial experiment, or what mathematicians may call a Bernoulli experiment. It's the same set of criteria. And if we know that fixed number of trials and we know that probability of success, it turns out we can analytically calculate the probability of getting any number of successes out of that fixed batch size, that fixed number of trials. And that's really going to be the fundamental calculation that we will do to base our probabilities on. So the binomial random variable is this number of successful trials out of this known fixed batch size given a fixed probability of success. So for any binomial distribution, there are two parameters that are of interest that define this particular binomial distribution as opposed to any other binomial distribution. And those are n, the number of trials, and p, the probability of success. And then to make our calculations, we need to know, well, what's the value of k that we want to find the probability of? And again, we use k as that just as that placeholder, as that name for our discrete random variable. In Excel, it turns out there is a function that allows us to implement this formula, this analytic formula to calculate the probabilities for associated with a binomial distribution. And that formula in Excel is called the binom dist formula. And that formula has 4 arguments, 4 things that we need to put in. K, which is this value of this discrete variable we're interested in. In our example, it would be the number of heads out of a batch size, out of 10 coin tosses that I'm interested in finding the probability of. N is the number of trials, and P is the probability of success. So those are the 2 terms that define which binomial distribution I'm talking about. And then C is a flag, if you will, that tells tells Excel whether or not we want to calculate the probability of being exactly at a certain value, K, or if we want to calculate the cumulative probability starting from 0 and adding in all the subsequent probabilities up to K. And I can either make that true or false, 1 or 0. So for example, if I want to know the probability of getting 7 heads out of 10 coin tosses, I would use the formula equals binom dist 7, 10, my number of trials, 50%, that's my probability of getting heads, and then I would set this cumulative flag to 0 because I said I want to find the probability of being exactly at 7, of getting 7 heads out of 10. So I would set the cumulative flag to 0. If instead I wanted to know the cumulative probability, so I want the probability now of getting 7 or fewer, okay, I want to get the probability of getting either 0 or 1 or 2 or 3 all the way up to and including 7 heads out of 10 coin tosses, then I would say binom dist of 7, 10, 50%, 1. So I'm just telling with that cumulative flag at the end, I'm telling the binom dist formula, do I want just the absolute probability at K, or do I want the cumulative probability up to and including K? I want to take a look at one other aspect of this function, which is something called, you can think of as the inverse binomial function. Remember when we calculate cumulative probabilities, it's the probability of being up to and including a certain value of K. Well, there's a function that lets you sort of work backwards. If you know the cumulative probability and you want to find out what value of K does that correspond to, the function in Excel that does that is called a crit binom function. It's kind of the inverse. So instead of putting in K and getting a cumulative probability with that cumulative flag turned on, crit binom assumes you're dealing with cumulative probability. You put in that cumulative probability and it returns the value of K. Technically, because it's discrete, right, those cumulative probabilities are going to increment. They're not going to increase continuously. So what it returns is really the smallest value of K, for which the cumulative probability from K down to 0 is just greater than the probability value that you put in.